Okay, second part, we're going to get into datum references and position tolerance. Alright, so, okay, so when we deal with the datum references and then your position, tolerances, we're just talking about, hey, this is what we're concentrating, here is your position, there is your tolerance, and here are our datums, datum references. I just call it datum, so this is primary, secondary, and then your tertiary right there. Since we're dealing with the position, you can have MMC at the datum, reference as well. So when we think about the feature of size, feature of size are just the size of all of your features on your part, and you're gonna have like a reference, datum reference, in feature control frame given to you like that. So this is kind of like giving you the information of that tolerance, what tolerance control that we're doing for this, tolerance, what kind of material condition we're looking for, and then where are we measuring or verifying from, which plane. So that's what you're seeing right here, So at that time, we're gonna do the RFS, so that's regardless of feature size. Unless you give like this, either at max or least, material condition. So always think about it, your feature size got to be at, okay? RFS, regardless of feature size. If you have your M, then it isn't. If you don't have the M, it is at RFS, okay? Because when you think about material condition, these are modification. So without the modification, you'd be at RSF, all right? RFS. So try to get that point. Don't know where is RFS? Your RFS is without modifications. So with modification, you're not at it. Okay, very easy. I think to me, I think what is getting to your brain is your terms. Terms are very difficult even to talk about it. It's not familiar to you, and just take it slow. Do repetition. So if you do repetition, you will get it. You can get it at one time, by the way. You will be so confident. Doesn't matter how smart you are or good your memory is, you still need to do repetition, to be able to actually get these very, very difficult terms. And that's why the engineering field, technology field, engineering and technology, if you combine two together, engineering technology, it looks like easy field, but it isn't, because you got to know engineering side, also you have to know the technology side. We're not like pure technology, we're not pure engineering, we're in between, okay? But then you gotta know both sides, by the way, so that's a lot of stuff to do. And that is why you get paid sometimes, some of the company more, than the engineer or more than the pure technology side. Okay, so we already knew, from the last part, which is part 1, every time we use our bonus tolerance. Why? Because we have modification, modification to it, because you're dealing with the MMC, so therefore you always have a bonus tolerance. You can't just go with your RFS specified tolerance, you need a little more to deal with your max, because your error is too huge. It's a worst case scenario right there for you. And when your datum reference is a feature size modified to MMC, you're gonna have a shift of tolerance. That's why you need the bonus tolerance to compensate for that error. Okay, now we're repeating the same thing. If you don't have any kind of modification, MMC or LMC, just go with RFS, which is regardless of feature size. So that's your rule 2. Your feature size, you can select that as a data. We're gonna refer to the datum feature axis, medium line or plane. Why? Because datum is a point and axis or your plane, okay? So that's why you can do any one of that if you want to use a feature size as a datum. Your datum ABC, etc., etc. And your variable gauge got to be used to establish the datum axis or center plane of datum features of size, and they're not modified to MMC or LMC. Okay, so that's just telling you how we identify these datum planes, or axes or points. To make it easy, every time you want to identify or establish the datum, point or axis or plane, we're going to use physically the gauge, yeah? At least you got it in the lab. So when variable gauges are used to verify a part specification, we're going to make sure that your gauge is in contact, yeah, with your target datum, point, plane or axis. Try to make it, you know, as perfect as possible, meaning like we don't want a shift of tolerance when we're trying to verify the tolerance. Okay, all right. So your manufacturing and inspection your datum feature of size at your RFS is a more demanding requirement, okay, than a datum feature of size at your MMC, because your verification got to be done with variable gauges or gauges with your moving part. Yeah, we did this like several times already, so you should know that by now. So we use the fixed, yeah, functional gauges because they can simulate the mating part. Most of the verification purposes that we do, yeah. So for position tolerancing your MMC, your maximum material condition size feature datums, you gotta use them whenever that's possible, yeah. Meaning you need the datum for MMC, so the more accurately simulate the worst mating condition, yeah, for assembly of the parts, because they can simulate, yeah, more with more accuracy for these worst, you know, mating conditions. Meaning we're considering the highest error. And we are going to use our RFS, which is your regardless of feature size datum. And you use it only when, yeah, your design requirements don't need your datums at your MMC. Yeah, so without the MMC, so no modifications, and you can use your RFS. Again, this is just a continuation of your review. So your tolerance control is usually most often established around your feature axis or your center plane, yeah, when you deal with your position tolerance. And then you don't have a bonus tolerance. When you deal with your RFS, yeah, you don't need the bonus tolerance because your original, yeah, tolerance applies. You can do it at any incremental size, yeah. Only with the MMC, when you deal with that, which is not your RFS, then you need the bonus, yeah. For just a regular RFS, yeah, when we apply that for this tolerance positioning to it, you don't need the bonus tolerance. So your part verification again gonna require the use of your gauges, yeah. Because without the gauges, you can't be able to verify. Yes, you can be able to verify these dimensions, yeah. All right, now let's get into tolerance of position. Now we're gonna study only your regardless of feature size without MMC stuff. So let's get into here. So here's the tolerance position, which is this little, yeah, location right here. And of course, feature control frame is right here, yeah, and that is with your RFS. So that feature got to be located on a true position, yeah. So here we have our cylindrical tolerance zone. It's given to you. The value is 0.014 inches, yeah, on the diameter. Because that's set it so here with this little symbol, and we're dealing with the position tolerance, yeah. So again, your datum references are A, B, and then C, which is here, here, and here. Don't forget we are in different view. So some of the surfaces you can see in a front view, okay, only on the side view. Since we're dealing with the RFS, you don't need the bonus tolerance, okay. We can just go with what we have for like a 0.014, and for the whole, yeah, the whole diameter is going with a 0.4902, 0.5, yeah. Here these are your significant figures, so you can go with the accuracy in the 3 decimal points. Okay, so let's take a look at it. So now we're going to come with the same thing, true position. We're going to identify that width by using a 2, two planes. We have a 2 basic dimension here and here. Don't worry about the value. Now we're going to box it with a little circular yellow circle, which we call that the location, tolerance zone, which is your RFS, because we're not dealing with any kind of modification on that material. So we'll just go straight with our true position and with the given tolerance. Now we're going to deal with the worst position, worst possible condition, and your whole axis, which is right here, got to be located at the extreme limit of your cylindrical tolerance zone. Now we're going to give it the blue, which is here, and that's your MMC diameter is applied, and here is our little yellow circle, which is your location tolerance, RFS, and then here is our true position. So when that axis is located at the extreme limit of your in your previous slide, limit of your tolerance zone, your MMC whole axis would be offset, from that from the true position. So it's going to come out from the true position about a distance equal to 1/2 of that position tolerance, which is 0.014 divided by 2 is going to give you 0.007. And then we're going to throw our LMC. LMC is the least material, so we chunk the material out, so your diameter is like way bigger. This MMC and LMC are not in the control frame, okay? There's no M here, all right? So there's no modification whatsoever to that true position. This is just showing you where your MMC and LMC could be, so you can be able to understand where this axis location is. See like how far away that is, So the location of tolerance zone is our RFS, Now we're going to draw our white circle right here, and that is your MMC boundary. And your center is right there, the little blue one, And of course, the white one is represented right here, So you have a 2 center right there. Of course, we have a 3rd center, which is also the same for this 2 little blue one, sharing the same center. So you can see no element of that whole surface can be inside of that boundary. So you can see like blue lines outside of it, So this is your MMC boundary, meaning like the MMC can't come inside of that boundary. Why? Because we're dealing with the RFS. RFS has no material modification. So if you had like a material condition, that would have been like this circle. But right now we're gonna deal with here, because your MMC and LMC, if we got them, that would be outside. Right now we don't have it, so then we just go with our straight RFS, which is this boundary, meaning like your actual part will never be drilled here or here, it will always be here. Okay, now we're gonna bump up, which is another boundary, which is this guy, So for LMC diameter, even though this blue line is here, and this is your diameter for LMC, and that's for diameter for MMC. But when you look at the boundary where that LMC can't come out, is here, So your LMC cannot go, cannot be able to go, meaning like the whole diameter cannot go over that boundary, okay? But then again, we're not dealing with the LMC or LMC, so your RFS, gotta be free of that material conditions when we do that. And this is just showing you how it's not actually happening on your part, Your part is without the LMC or MMC, This is just showing where they could have been. Okay, so let's see how it moves around the tolerance zone, one by one. So he animated it, see like how the movement going, yes? But it's always stay within this 2 white, lines right there, So it's just a lot of slides, but it's just showing animation anyway, how he's moving around this 2 again and again, But you can be able to see that's within, the MMC and LMC boundaries, Not going to hurt the true position, which is your RFS, which is this little one right there. And you can see, of course, this is an exaggerated diagram, so you can see the hole is so far away, but not actually, in physical part outside. Of course, this is very, very close, to your true position, which is this one here. All right, so tolerance position at maximum. Now we will call the real maximum material condition. So let's get into here. And here, MMC, so therefore we need a bonus tolerance. So we're going to have this example in our datum, your datum frame. We have material condition, which is at max, and we have the hole diameter, which is here. Tolerance diameter, of the position of that feature is this one, okay? Position meaning it's got to be here, located here. But the size of it is controlled by this, Okay, so now let's get into two planes, your true position. I will show you a little more faster, because you have already seen it several times, your MMC diameter compared to your true position. Then we're going to start giving our tolerance location, from the true position. And then we're going to have our bonus tolerance coming out of the true position around it. So this little mesh area right here, see that? And that's your bonus tolerance. Bonus tolerance meaning, hey, you have a more space that you can make mistake. Meaning like the position of that hole can locate it anywhere here, It can move around instead. Okay, now let's see slide by slide, how the MMC boundary. This is your LMC boundary. Now we're going to start giving you the LMC boundary in white, and then your LMC boundary in white. These are all of your diameter is in the blue, okay, drawings right there. So blue lines or blue circles, it's going to go move around. These are what variations about. So they are all, when you do parts, right, manufacture the part, it can be there, it can be here in different parts, it can be there, but then of course still in our tolerance zone, even with the MMC material in it, okay. So now your actual position of that hole can be anywhere like that, okay. All right, doesn't matter where your MMC diameter or your LMC diameter is, we're still fine, because our mistake is still within the allowable zone from here to here. Okay, then we'll go into zero position tolerance. Zero, okay, position tolerance. And then we're going to do with our MMC. So zero, so now we zero out our tolerance zone right there. So you have your minimum hole and your maximum fastener fit. Your fastener is going to go right into fasteners or your screws or your bolts, going to go into that hole size right there. Now we're going to deal with a zero position tolerant. Your position tolerant is at zero. Here you can see in this control frame, you have your datum reference A, B, and C. So you have your A right here in the side view. The front view, you have your B and C right here. And we're dealing with this, a little, see the feature, which is your hole right there. And when you actually look at it, we also have a symmetry, in this part, of course. But of course, we're not going to confuse you for that. All right, so let's get into position tolerance. We're going to control your planar applications. So here, position, and here is your diameter, 0.6, okay? We're at max, and 3 data is going to control. So the tolerant position principle, you're going to apply that to the planar features of size. Feature size means like it's just a plane, and your diameter symbol is going to be removed from the feature control frame. We always use this, Now we're going to get rid of it. So now without the diameter control, in the control frame, without the diameter symbol like we always use, yes? So why? Because we're doing controlling the plane, now getting into the plane. So the tolerance, so the resulting tolerance zone is going to be established by 2 parallel planes, So therefore we get rid of our diameter symbol out of it. And that 2 parallel plane is going to be separated by a distance equal to that tolerance value, which is this distance, in this case is 0.6. And you have your modifiers, of course. Since you have a modifier at MMC, you do have a bonus tolerance to compensate for the extra errors, Okay, so now let's get into this part. it's kind of like a symmetric for me, dealing with the position tolerance, and we're gonna do with the plane, control with the plane. So we have a symmetrical features right there on this side and on that side, and that's your center, and plane right there, we have this plane and that plane all together, and we can be able to see the same plane in different views, So in this case, our feature size is 8.8 all the way to 8.0. Tolerance of that position is going to be 0.4, that you can go up and down, And so it will be like a 20 to 20.5, millimeter. That is your feature size dimensions. Your center plane is going to be right here, So your 20 and 25 is this dimension is your part size, So from here to here. Your upper and then your lower. That's what it said right here, feature of size. And we have a two, datum reference. One is R and the other one is N. You can give alphabetical symbol. It doesn't have to be always ABC. Of course, we don't use Q for the datum, by the way. So anyways, let's go to the next. Now we're gonna go into exaggerated, So you can see how the center, plane is going to vary like this, vary like that, It's just showing you different views. So it's they're the same thing, by the way, seen from that side and seen from that side view. Okay, this is a front view. So that two planes got to be perpendicular to the datum plane R, which is here. This is this one. When you look at it from the side, we can see this hole. Okay, right here in there. So this surface is in the back of it. In the back of this front view. All right, now let's get into here. Now we can see a little bit better. A different part right here. And our plane is right there, your datum center plane K, which is right here. This is our datum plane, and the other one is J, and you can see it, in the other side view. You can spot this one from the front view. You can see the inclined surface from the front view, but you can be able to see it from the side view. So make sure you review your MET 101, drawing, engineering, drawing principles. So anyway, so your tolerance is 0.2, apart. Then your size is 8.8 to 8.4. We're at the maximum material condition. Okay. Then we come here. We can see our zones right there clearly. So that plane can be able to vary in that zone. We talk about that all the time. You have your two parallel planes. Where there's a position. Again, don't forget you're dealing with the position of this thing. Okay. All right. And then we get into the group feature size. So right here, so I just copy and paste it right there for you. And here your MMC. So that's your datum K, which is this guy right there. And your LMC is going to be here. Your MMC is going to be right there. Okay. So your width is going to go from, you have starting from 8.8 is your 8.8 is your max, and then we're going to go down all the way to 8.4. Okay. Your datum K, the way that we write the MMC is a little bit difficult because of this feature size. The feature size is here 20.5. So that's what you're seeing. So trace this line for that. The chart is going to show you the value of the size, so you can see from 8.8 to 8.4, 20.5 to 20, okay? That what happened on the height of that object, which is this one from the front view. And then the growth side, which is this growth right there, the size is going to depart from the MMC towards your LMC, okay? So here we're dealing with the two. One is the size of the part, and the other one is the growth size, which is the feature size of that part. Okay. Okay. So position, multiple symmetrical feature. We're gonna take a look at MMC. So we have multiple symmetrical features in the part like this. So now take a look at it here, 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 and here, here, and here. So now we have an 8 of that thing going on at 6.0 all the way to 6.2. Then we have a different tolerance given to you. So when you look at it, just go through your data line right here, which is your leader. Here also, so this little, see that part right there is 52 in diameter. Your first, they all share the same center anyway. The second one is going to be diameter 20, okay? And then we have another, which is diameter 40. So it's not as big as your first, diameter, and the second diameter of that circle is a 40, and then the tiny one right here is a 25, and then the corresponding tolerance are given to you as well. So when you look at it from the right side view, you can be able to see the cylinders for these holes right there. The first one, second one here, which is this one. And we're dealing with this little, see that 45 degree here, and that's the 8 of them in there. So dimension, location, relationship, you can be able to see it between your features of that part, and then your number of instances, how many times, okay, followed by the size specification. So you should be able to read these things by now. I don't want to talk about it again and again. All right, then we go into identify and label the datum. So we have right here D, and we have another one E. Okay, so we're dealing with the 2. Now we're going to bring our control frame right there for your position tolerance 0.5, and then your references, which is D, and then your E right here. These are your related datum, DE, and then your maximum material condition right there at M. All right, so that's your location symmetry, symmetrical features, multiple, and we can locate them in that way by reading the corresponding tolerances, sizes, and then of course your material condition and your datums. Pretty easy. So then now we'll get into non-parallel features. So when we deal with the non-parallel features, your hole's got to be placed at the angle to a surface, right? So at that time, so there are instances where your axis of your hole is not going to be parallel to each other. That happens in manufacturing. So let's take a look at this example. And here's the part, and this is you're seeing the section views, so we can see the section lines right there. A little bit complicated for you, but just go slow. We have 8 of them, which is actually this one anyway, So we cut it out and we can see inside of it, So now we have section AA, and then this one come, out of this part, and then of course we have a side view for the front view. So we have 4 times of this, and then you have your datum is going to be AB right here, and your B is right here. Go very carefully. Your tolerance 0.2. Your diameter, which is your tolerance diameter, and that you're going to trace your size. Size is 8 of them is going on for that growth right there. So it's going to go down all the way down to here. Look at that, So your size identify right here. That diameter got to be 8, and then you have 0.2 for upper, and then 0 for your lower. Limits right there. The next one is here, identify right there, and we can be able to read each one is sharing the same data reference right here, and then here, because it's the same part anyway. Okay, so that's your angled, the angle is, again, I'm going to point that out for you, which is here, right there. Okay, you have 1, 2, 3, 4, 5, 6, 7, 8 of them, angled, and then your non-parallel. These are not parallel to each other.
I didn't catch that.
Then we'll get into position tolerance at LMC. So when you get to LMC modifier, we're going to apply that to a tolerance position, and you're going to have that tolerance applied when the least amount of material is left in the part. Meaning like the least amount of material, again and again your part is losing material, therefore your feature is gaining, the width. So here in this case we're dealing with the shaft, so the largest hole with the smallest shaft. Okay. People kind of get the hole and the relationship with the material, but they always have an issue with a small shaft. Okay, don't worry about it. If you have like a largest hole, meaning like you have a least material on that part. Okay, since you have the least material, yeah, on the part, you're gonna have a smallest shaft because you are not dealing, with the material only. What we're concentrating here is your tolerance. Tolerance is a separate zone. That's why you have the smallest shaft. Okay, because you still have the tolerance position for that hole because the hole is a feature on that part, and we're dealing with the position tolerance of that hole, not the hole itself. That's why you have the smallest shaft, because we are considering or account for the zone of that tolerance around that hole. Okay, don't forget that. It's a very, very, very powerful. uh, so of course, for engineering, drawing, drafting, as you go advance on, it get harder and harder because of these little things like that. You have to remember all these things in your head all the time. Initially, you won't, so please make sure you have a pocketbook. Okay, I tell you every chapter to buy the pocketbook. Don't spend your money to other stuff. Make sure you buy your phone, your computer, you need it, your monitors, yes, and a pretty good mouse, and your pocketbook. Okay, you need to go back to all the time. You can have the internet, so you need it with you. Okay, all the time, please. All right, then your position tolerance at LMC. We have a least material condition modifier. We will use it to control the minimum wall thickness, of a part, and then you're going to maintain a minimum distance from the edge of the feature as a whole, and then you're going to control the minimum stock for machining on casting. Okay, that's just a machining procedure or process. Of course, your variable gauging or open inspection techniques, you're going to need it for verification. Anyway, don't worry about it. Okay, we're going to see one by one. So we're going to start with this position tolerance at LMC. So here is your tolerance zone and your two planes right there. We have our dimension right there, some value right in there. Don't worry about it. It can be any value. We're just looking at the true position of the hole, and then we will look at the tolerance zone at LMC, so least material condition. So right now you can see this is your hole size, maximum diameter, so therefore we're dealing with the least material condition. Then you have this little center right there, so true position, and here is your little blue, see that, and that's your least material condition. Okay, and again, you're not dealing with the diameter of the hole, you're dealing with the position tolerance, all right, of that. So don't go fast, go very, very slowly. Okay, to be able to understand what is it that you're looking at. I think students usually look at the diameter instead of the position of where that hole is going to be on that part. Okay, where it is on the part. Where it is on the part is not equal to the dimension of its diameter. Okay, location, we're dealing with the location, position. All right, now you're going to have your tolerance zone. Again, this tolerance zone is not the diameter. This tolerance zone is the location. That's why it's a little bit difficult for you to really see your LMC. Okay, so your LMC true position, that's your tolerance zone that you can vary in that zone. And then here is your hole size, is your maximum diameter LMC. Okay, now let's get into the position tolerance at LMC. So I'm going to show you the slides, one by one, so you can be able to see your least material condition and pay attention to the position. So this is your control frame right there. We're dealing with this hole right here and the position of that. Okay, so this is a hollow step shaft, and then you can see the minimum wall thickness is going to be 6.0. Okay. And then we have a two control frame with 3 tolerance right here. So we have two views, so you can be able to see the datum reference right here, it's at A, okay? All right, so now we're going to expand the pin. So you can see the shaft is going to come in right there, which we talked about here. Yeah, this is for the shaft. This is hole, so you can't see it. Now we're going to get into the shaft. Yeah, your pin is going to go straight in. Your pin is a shaft anyway. Your mandrel, that's going to establish your datum A right there. Yeah, which is going into this direction in the hole, of course. Pay attention to the view. Okay, this is a front view cross section, meaning I was looking at inside of it. And that pin is going to go straight into here, yeah, which we're looking at on the side of that. So your datum A is going to first establish using the variable gauge, which is this, yeah, come into contact with the part. Then we got our cylindrical, the green little zone right there. That's 0.4 because it said so, yeah. Here, yeah, right there, and here is your 25.4, your LMC, because it's got to be the largest hole, because least material that we are considering at that time, the smallest shaft that you are getting, okay? And then now we're going to get into here our theoretical boundary. It's going to come here at 25.0, and here is a 25.4, which is this guy right there, yeah, the maximum. So here is your little yellow one, is your 25.0, which is less than your 25.4, okay? And then get into 6.4 minimum bore. It's going to be right there, and that's dealing with the shaft, because your shaft can go all 6.0, and then now your minimum bore is going to be 6.4, okay? So the bore is, look at this, see, that's a very line, right, yellow line right there, okay? And here, right there to here is your minimum bore, yeah? Of course, your upper limit of your hole diameter is going to be 12.2 millimeter, yeah? And you're going to subtract that amount to your lower limit. The 12.2, you can't see it in this view, but you can see it right here, yeah? So there's this diameter right there. So subtract that, and you will get 6.4, and that's your minimum wall thickness for that. So where do we get the wall? We have to calculate it, yeah, from these specification, which is your 25 minus this little one, which is 12.2. Bigger one is right out there, yeah, and you will get 6.4 this thickness, yeah, for that wall. Please go over that so you can be able to see it. Yes. Okay, I try to bleach it. I'm very sorry, I can't bleach this thing. So every time I bleach this, I have to go each one of them, because he make it like with white, okay, so we can't fix the slide. But I don't know why he chose like the blue thing for anybody. I can't even print this out, by the way. Every time I print this out, it come out with so much of the ink, you know. I will be like using the entire ink cartridge right then to print this. So anyway, just do it with your, if you have time, go ahead and download, yeah, download with your textbook. Try to bleach it. I try to bleach it, but it takes a lot of time to do it. Sorry, I don't have that much of time to do. All right, so now composite and position, tolerancing. Composite is very important in specification and verification for quality, yeah, people. So let's get into that. So when you have the feature like your holes, yeah, and that's like arranged in a pattern. So when you have the pattern hole, then the location of that pattern it's not that important to design, yeah, the actual relationship between the hole and the pattern. So that we're talking about the position of that hole and orientation of that. So composite position, tolerancing, we gotta deal with that when you deal with your pattern stuff, yeah, with your hole. So we would locate the pattern, yeah, tolerance zone framework, and we call that the PLTZF. You will see that abbreviation because you can't write the whole thing, yeah, it's just taking a lot of space to write that. So if you see that PLTZF, please have your pocketbook, okay? So that's a pattern locating tolerance zone framework. It's going to control the location, all right, of your whole pattern. Again, not the whole. Now we go into pattern, yeah? So let's, sorry, I forgot to see your PLTZF example. So your control frame has a little, see that little additional box right there? And that's where we are going to put, okay, a different specification right in there. So the very first one is your pattern, and the other one is your feature, yeah, our regular features is put it into there. So if you get this type of frame, you understand that you are dealing with a pattern and the feature, yeah, size. All right, so let's get into that. Let me go and drink something. Okay, so we go into PLTZF. Some people is gonna call it Platts. Yeah, you will hear some engineers or technician called that way. So Platts and frats, all right. When we say just, but you can make your own. Yeah. So you can just go with pattern and just go with a regular feature. Yeah. In my brain, I just go with pattern and then feature like that. So in your brain, you can go with the Platts and frats, yeah, or like that, or a scientist from the German scientists, they usually use a Platts and frats. So I think it just suits their language. For us, we just go with the feature here and the pattern here when you do locating these parts or features on the part. So anyway, in real life, because it's harder, not everybody can do the work of an engineer or engineering technologist, is because you will not be getting only one control frame, yeah, or a little tiny bitty part like that. You're getting a massive, massive amount of features on a giant part or the entire assembly. Okay, so if you open a computer, you can see how many features right in the tiny little stuff. Yeah. If you open any kind of a product in your home, from furniture to whatever, incredible amount of features on it. Yeah, so don't take it lightly. Some of the students, they're not successful outside in the real world, and then they blame it on the professors or teachers because their brain cannot handle that switch. Yeah, so the switch is studying with a little thing. When we try to study the fundamentals, yeah, you don't even do well for the fundamental stuff. How can you be able to solve the complex, the real world complex design? You can't. So I got to tell you, you have to study. This is not a joke. Okay, that's why millions of people, all right, only one person is chosen out of that to do a very important work. Okay, and so that person will stay in the position for the next 40 to 50 years because he or she can handle that complexity. But not everybody can handle that complexity. Yeah. Even for the professor, we have to put a lot of time to handle different kinds of complexity in the part that we do. So again, it takes time, and I don't want you to be lazy when you study, because studying is not reading. Studying is not just looking. Studying is not listening. You have to do all of that plus actually draw it. Okay, actually draw with application or with hand. Of course, when you're learning, you gotta do it with hand. We force you to do it by hand. That's important. Okay, because you gotta familiarize yourself with, first of all, like trying to familiarize yourself with the term itself is taking a long time. Yeah, the term itself is like taking, because you have so many definitions, so many terms, so many different conditions, so many different combinations, sets and sets of situations that you have to think about. Yeah, so it's not a joke studying. So many people are trying to do it by taking care of family, kids, and taking care of everything. You can do that. I'm so sorry, I got to tell you this, all right? And if you can't be able to do that, you've got to make time, to study it. I feel so sad that sometimes I don't want to say this, but then I have to sometimes because I am in the position of teaching. I gotta tell you that you have to make time to actually get these material. Otherwise, you can't apply that knowledge in the real world, and you're gonna make serious mistake. Okay, all right. So I want you to take time to study. Take it slow. You can't get these things right away. That is not the fault of the teacher, not your fault. It just, they are too much. All right, they're too much. We gotta take time. it takes about 8 years, at least 8 years, to finish from BS all the way to the end of PhD. Okay, that's a lot of strenuous every semester studying 12 to 20 credits. That's a lot of studying. We don't get this. All right, we don't get this easily, by the way. So some of the people will like say all kinds of like horrible stuff at you, but scholarship is same as work. Yeah, you don't get these things easily. Of course, some of the institution just give it to you grade and stuff. Even we have to do it here, yeah, because we care about the student. But I don't want to do that too much because it isn't good for you. It isn't good for your career. So the only thing that is going to save you in your life is to actually study, okay? And you can't get it being lazy, by the way, okay? I do my work the first time of waking up all the way non-stop, all right before you sleep. Sometimes it's just like you have to rest like just completely like tired on the bed like that. But then that is the amount of work you have to do. Otherwise, it will never go into your head and retain it. Okay, so and don't throw away every semester. You have to keep your textbook. You have to keep everything that you do academically studying at school. Yeah, you can't just sell the textbook and get money out of it. No, don't do that. You won't be successful. Every subject you have learned, you have to learn next 6 months or 1 year. Yeah, so because one semester is a very short time, and you have to deal with about 3 or 4 books, right? You can't do that. Human brain cannot handle that. In addition to your own life going on, yeah. So don't throw away your textbook. Don't throw away the professor handout. We're trying to put it now the open source. Yeah, open source are we gotta give it to you because you can come back. Some of the students will come back to you because you need that continuation, repeated learning for you to actually get it. So don't blame on professor for open source stuff because you need it. It's for you. Yeah, our primary interest is you. Your success is so important for us. Okay, and I don't want you to waste your time and money. You're coming to school for doing nothing. Yeah. So make sure you study, 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 regardless of whatever that is going on in your life. You just have to function. You have to train yourself. You have to get that skill. You have to function. Doesn't matter whatever that's going on. And sometimes it's the same thing. We're all human. So we have a sad day, we have a happy day, we have depressed day, we have all kinds of different things going on emotionally and physically outside. But try to petition yourself to do the work. Okay. Otherwise, you will failed. Okay. So make sure to be successful. There's a lot of hard work in it. Successful people, they do extensive amount of work. They work on their career and their stuff continuously. Every free time they have, they do it, and you have to put that much of effort in it. Okay. uh, if you're like just smoking and drinking and fooling around, it's not gonna work, period. Yeah. So this 2 years, please give all of your time in scholarship. Yeah. Okay, I'm doing advising. I know I gotta say this again. I'm sharing with the lecture like that. So anyway, so let's go back to here to the composite positioning. We're gonna combine composite to simplify it. We're gonna combine two, yeah, two tolerance like that. So already show you the very first tolerance like that frame. I am totally tired of fixing this the spelling stuff and grammar stuff because we gotta write to the Microsoft, yeah, and Apple also, because their spelling is always checking for English. English doesn't work in the technical writing, so they gotta put the spelling check, spelling and grammar check for technical science writing, because all the English stuff is just a mess of everything that there is. We gotta use a passive voice. We can't just go all the time with the active stuff. So when you do the research writing, it's just a mess, like massive amount of horrible stuff going on in the spelling and grammar check. And when you apply that to the international student, oh my God, God bless them. Yeah, good luck. So they already have a massive confusion. No, you don't have to follow every spelling and grammar check that there is in the world because they are written written based on the English literature. Yeah, it doesn't work to detect the how can I say, to check the spelling and grammar for the technical writing. Yeah, so it's even make it so worse. Like when you read it, like the whole thing is like a mess. Like, and that's what most of the graduate students are facing, by the way. So anyways, I am so tired of fixing all this stuff right here. So anyways, let's go into here, and that's your plus. Yeah, dealing with the pattern, and another one is your phrase, dealing with the size of the feature. Okay, then let's get into here. Let's go there. So now you see, I hate this. I gotta do this again. This all the automation just messing up. All right, here we go. So your diameter, yeah, 0.4 for the pattern, and then 0.15, yeah, for the size. So let's take a look at it in a diagram for this part. Yeah, we have all of this, and you can see that the composite tolerance giving you the information for these tiny little holes right there. Yeah, this is smaller than that. And we have our y right here, and our z right here, and then your x is going to be on this view, on this side. Yeah, so try to practice your different views, and then locate your data, dealing with the pattern of the hole, location of the hole. Okay, so the location of the pattern of that hole, and the location of the size of that hole. Okay, all right. So first we're going to get into the very first, which is this side of the part, and that side we're not dealing with the symmetry, so we have to go each one of them. Yeah, so the very first one is this one. So when you look at it, your plus and frets are right there, controls. They're controlling the location of the whole pattern, and then your interrelationship between the holes in the pattern. Okay, so that is going to give you your composite feature control frame, which is this guy, which is a little bit different from the very first regular control frame right there. Okay, I'm getting tired. Okay, so anyway, so that's your application, yeah, right there. Then we'll get into a bigger exaggerate. Yeah, we're gonna exaggerate this side of that part. So you can see a big diagram like this. So here you can clearly see your diameter. Don't worry about the tolerance right there. It's just giving you the size of it. Yeah, we will get into the pattern is going to go 0.4, and your whole, all right, diameter is 0.14. Yeah. So what is the difference with this and that is, like when you deal with the pattern, we're talking about how these holes are located and what kind of pattern. Are they in series? Are they parallel to each other? Are they stacked one by one? Are they going in a array direction? Yeah. So when you look at it here, we have like a 1, 2, 3, 4, and they are located 4 hole pattern in this way. Yeah, for this example, and that is located away from these datum XYZ like this. Okay, so it's just like a 0.4 away from each other. So that's what it's talking about. Yeah, so 0.4 millimeter in diameter for the pattern. So 0.4 is bigger than your little this one, yeah, which is only like a 0.15, yeah, 0.15 diameter for this. So 0.4 for the pattern is this distance away from each other. See that? Yeah. That's what we're talking about. Okay, so I think you should be able to get the pattern diameter, and then you should be able to get the regular hole diameter. Yeah, right there, and where they are. So in easy way, let's take a look at this. And we have our planes crossing to the center of these holes. Yeah, so our coordinate will bring our coordinate location right there. So I have our XYZ datum right there, 0.4 for the pattern. So theoretically, we're going to take a look at this. So XY hole pattern location is position, yeah, with your basic dimension. Don't worry about what the dimension value is. We have some dimension right there. Just remember that. And then we're going to reference that to our XYZ plane, yeah. So now we're going to come in showing you with this little yellow, yeah, circle right there for each of the hole, and that's going to show you for the pattern location, yeah. The pattern location of that. So when you look at it, this is a 0.4 tolerance zone for the pattern, okay. So here, from here to here, there is a distance, yeah, away from each other, and that location got to be, you cannot go over 0.4 tolerance zone, yeah. So now you can move away, of course, you know, your cylindrical tolerance zone, these little small crosses, little things, see that? And they can vary in that zone, okay, in that plot zone, which is your tolerance 0.4. But it gotta be within that tolerance zone, can't go out of it, yeah? If you go out of it, you're gonna have huge errors in your dimension. Okay, tolerance dimension, of course. And then, of course, now you're gonna have a misalignment if that's going like this. And this is, of course, again, exaggerated, yeah, drawing of that. So now we're gonna connect this little blue one with blue one with the blue center. See like how the alignment just became off, yeah, totally offset from the true position of that, yeah. Okay, then let's go into the next one, which is your feature, yeah, relating to the tolerance zone, which is this guy right here. See, we have now the blue circle right there, each one of them, yeah. So now we have little yellow pattern. Now we have a little blue one right there for the diameter of that hole, okay. And that's like only like 0.15, yeah. So when you look at the yellow zone and the blue zone, you're seeing the larger pattern locating tolerance zone on this drawing layout, okay. And what you're seeing is a feature relating tolerance zone, which is the blue one, yeah. So the feature related tolerance zone blues, they are within the pattern location, yeah. So that way you won't violate the pattern of that holes right there, yeah. So patterns and feature got to work together. So they have, because they're interrelated to each other, yeah. That's why we use a composite tolerance. Otherwise, it's not gonna work, yeah, in your part. Okay, so now when we take a look at our composite feature control frames, we can be able to see our frets and then our plats. Your plats is the pattern, your frets is your feature, yeah. So we just, or you can also go with the P and F. So you can see how the feature is inside, yeah, of the pattern tolerance zone right there, yeah. Of course, this is your actual whole size right there. The yellow is the position, okay. Yellow is the position, pattern, and then the blue is the position, and then the white one is your actual drill size, okay, for that hole. All right. Alignment also depends on your tolerance, because right now we're gonna get into our coaxial features. Of course, they are related to each other, and in this part we have a little hole right there, and we have a composite tolerance, yeah, control frame telling you about that hole. So first one is the pattern of it. You can see the pattern by looking at your front view. You have to take a look at the entire part from the side view, yeah. So from the side view we can see all of this related, pattern right here for this hole. So let's go from this part, that, and then this, and they're disconnected parts, yeah. See, very very important, they're disconnected but they're in the same position because we have only one, yeah, drill hole right there, bang, going through, yeah. So here, that's our base, and so the pattern is important to and then pattern location is as important as your feature, yeah. So that's your plats, and then that's your frets is right in there, okay. So we have a 3-hole linear because they are in line, yeah, linear pattern, and this thing, your part is a hinge, yeah. We're going to do our true position, of course. So let's get into it and take a look at it. And here is our controls. So our controls 0.4 for pattern, 0.1 for the for this, yeah, size, and then we have 3 of them, and its own size, yeah, which is 6, and then its tolerance is plus 0.2 to 0. Then let's go into here. So you have your linear coaxial feature alignments right there, and we're gonna have our section view, yeah. and you can be able to see this in a cylinder right here, disconnected cylinder. Of course, your axis is right here, yeah? So that tolerance zone 0.4 diameter, and it's going to specify for that 3 aligned holes right there. And then the axis of all of these holes got to be within that tolerance zone. Otherwise, the alignment is going to be so off, yeah? And they're all coaxial to each other. So when you look at the plus, yeah, and then your frets, you have a datum reference, which is controlled by this plane A and then that plane B, yeah, all together. Now we're gonna get into it, and we will give the zones, yeah, and then here is the little shaft that's gonna go into these holes, yeah. Okay, so when you see here, you're gonna see this little red thing. See that? So that's your red cylindrical, because you can see the cylinder right here. Zone. It is a zone because we mark it. You know. So that's your feature relating tolerance, because they are related because they share the same size of that hole. Okay. So we also share of course, the same size of the tolerance for each part. 1, 2, and then 3. Of course, they are centered within the boundaries of the larger pattern, which is this, yeah, this little, yeah, see the locating zones right there. And the pattern is always larger because it's 0.4 C, and this one is the size of the hole, which is your diameter is 0.1, yeah. And we're seeing, looking at the position and then orientation. Position and where is it? Orientation and how that is oriented in 360-degree around, okay? So in English word, position is a place, yeah? Orientation, how is it placed, a placement or a direction. Yeah, I call this how is it going, like direction, that's a location, yeah, where it is. Okay, you can of course define in the way your brain takes it, okay? So here we're going to consider account for the worst case scenario. This is pretty bad, yeah? So this is just exaggerated, of course. It can't be that off in real life. These are little tiny variation that we are drawing in exaggerated diagram. So this illustration is going to show you the worst case for alignment is so messed up, yeah? None of them is the same. Oh my gosh, bad manufacturing. So then you have like a 3 hole, 1, 2, and then your 3, yeah, 1, 2, and 3. So the whole axis got to be within the red tolerance zones. They are all positioned, yeah, relative to your datum A and B. So now we're gonna get into the hinge pin and put it into these holes, yeah, right across. So we can see the 3 holes. Look at that, yeah, without any kind of interference. And here is your shape right there, going through each of the hole, and we are definitely applying this composite tolerance, yeah, for that. Okay. Alright, so let's take a look at the example. So we're going to go from slide to slide so you can see the changes for your plus and your frets. Alright, so linear coaxial feature alignment is like that, and we already know 3 of them, bang, bang, bang. And here's a composite tolerance. Your datum is going to be A and B here, where we measure the verification, yeah, for these dimensions. And then our tolerance, 1, 2, 3, the size of this, the pattern of that, and then the position, all right, tolerance of that, the whole. Okay, and then let's get into here, yeah. So right here, the first thing is we're concentrating on the pattern. Make sure you understand the pattern tolerance is bigger, yeah, than your position tolerance, yeah. Position for the pattern is bigger than your position for the whole, okay. All right, then let's go into it, and we can be able to see that, yeah, which is your position. This is your frets, and that's your plats, yeah. Then let's get into the next one. Now we can see the limits of that, yeah, yellow one, and also you can see the center, which is your the whole axis right there, yeah. And there, of course, the 3 holes are within the 0.4 millimeter diameter, yeah, cylindrical tolerance throughout that part. Then we'll get into our red zone, yeah, which is your feature relating tolerance zone. Go into there so we can be able to see how, yeah, how it can go through these holes. but again, it's got to be within the a tolerance zone, limited, okay, which is, we call it allowable tolerance zone right there, which is controlled by this control frame right here. So your total feature relating tolerance zone, which is the red one, cannot go over your pattern tolerance, because pattern tolerance is bigger than your feature tolerance, okay, position of that feature tolerance. Don't forget, we are positioning the pattern and also the hole itself, okay, position. Students usually confuse the position with the size of it. Size is usually, you will see on top of that composite tolerance frame. So this is just telling you here, you can see the position where it is, okay. Now let's get into and see the worst case scenario right there. Your pattern located in tolerance zone. We're going to maintain it with respect to your datum A and B. Your feature relating tolerance zone is free. You have to float within that datum, these zones right there, okay, larger locating zone. So the pen is going to fit into that hole, but it's not going to be directly linked to that datum A and B. So let's see that. See, yeah. You have a two distinct zone right there. One is right here, and the other one is here. That's your pattern of the hole, and then this is your 0.1, and that one is a 0.4. See that, from this axis, okay. And your shaft, when you put it in, got to fit right in there, which that's what we're talking about. Your hinge pin is going to still fit into that hole, but it can't go over that range right there. Pay attention and know where you're looking at it, because you have nothing else but these features on that part anyway. Okay, and so right now we're putting in maximum material, so meaning like we want to leave the maximum the most possible material on the part. So your hole got to be as small as possible, as small as possible. So your shaft got to be as big as possible. Okay, now let's get into linear coaxial feature alignment. So after we finish the patterned composite, we will come into the alignment. So when you look at the holes, and if these holes they have like a different sizes, we got to deal with the alignment, of course. So their diameter got to be called out, to make sure that they're in appropriate view. And then your feature alignment got to, we got to think about the alignment, and they got to be identified in your composite, feature control like this. So here we have, in this example, 0.6 and then 0.3, 0.6 for the pattern, and then 0.3 for the position, of that hole, and we are dealing with the maximum material, So we have two coaxial holes right there, one and then here, Of course, when you look at it here in your right side view, you can be able to see it, right into it, so you can see the cross sections of material right there. And here, the most important thing that you need to understand is the size of the hole. Look at that, it's different, okay? Size of the hole, look at this, okay? They are different. And it says so here, one is this, another one is that. However, we are sharing the position tolerance, the same for the pattern, and also this 0.3, okay? Which is your tolerance for your feature. So your feature relationship is not going to it's not controlled by your datum reference right there, but it will be controlled by this composite tolerance, because your shaft gotta go through that hole, So you can make it so big like that because it won't go through here. So it's gotta fit this and that at the same time, So therefore we have to obey this pattern and also the pattern and the feature, pattern location, but it's got to be a coaxial feature alignment. Otherwise, you're gonna get into trouble for the fit. Yeah. So the hole sizes are different sizes, but they got to be aligned axially. They have to be aligned, meaning like this whole thing can be right here. This hole can be right down there. Otherwise, the alignment is not going to fit. Alignment is the best when the axis is totally horizontal. Yeah. Okay, meaning like 180 degrees got to be perfect, true position. Yeah. So that's your goal to align correctly in this example. Okay, I think you kind of get it. All right, so then we will get into counter bore holes. Counter bore holes are somewhere your fasteners are going to go into. So when we think about the counter bore holes, you have your location, your datum references, your position, tolerance for a counter bore axis. All right, is to be the same as the axis of the hole, because counter bore again is right at the hole. Otherwise, you can put the fastener into it. Yeah. So only one feature control frame, we're going to use it to serve that. So here's our control frame, and here's our position, and here's our tolerance with its diameter given to you. Yeah. Now you're dealing with the counter bore, so you can see these counter bore symbols right there, and you're dealing with 1, 2, 3, 4 of them. Yeah. So well, I'm going a little bit faster, but then we have already studied that in previous chapters. So we have our diameter, yeah, and then another diameter, because you have the original hole, and then you have a counter bore diameter with your head thing, yeah, and then your depth is, of course, your counter bore depth is going to go into that much, yeah. So we have our datum measure from your where's A, and then your B, and then your C, okay. Your front view, your top view, and then this is your front view. Then we're going to exaggerate and go one of this, and get into here, and you can be able to see this. So we have the true position sharing that axis and your height of the counter bore, and then here is your depth of the counter bore right there. So you have your major diameter, don't forget it, yeah, and your datum plane A, which is here, yeah. So now you can see how the counter bore's hole is where the fasteners are going to go into it, yeah. Your screws or bolts are going to get into that. The depth is here, and the diameter, major diameter for the head is there, right. Then here we start identifying the tolerance, yeah. So in our feature control frame right there, we can see our tolerance is 0.2, yeah. So that's your cylindrical tolerance, where your true position, yeah, can be able to vary in that tolerance zone. So that's your cylindrical tolerance zone for your hole and also your counter bore, because they're sharing the same, again, axis, yeah. So now let's get into it and actually take a look at that, yeah. So now we're going to separate the depth, and then we're going to separate the major diameter of the counter bore, 4 of them right there, yeah. So now we have a 2 control frame. So when you look at the clearance hole and then the counter bore specification, they're being controlled, with separate and feature specific geometry tolerances when it comes for the position or location, yeah. We're still in the position. Okay, now let's get into your true position, your datum plane, yeah. So that's your axis of tolerance, your clearance hole, of course. Don't forget your clearance hole. The hole is for clearance to make sure that your fastener go into that, yeah, hole right in there. And of course, you need to have some space in between them, because you can't get like a tight fit, or it can also be so loose. So the clearance holes is very important, yeah, in tolerancing. Geometry tolerancing. So the function of each is determining the factor in that type of the decision. Okay, so now let's put that in. So we have a true position, and we have another one which is 0.2 cylindrical tolerance zone for the hole at MMC, and you have your datum plane here, and you have a true position there, and you have your 0.5 cylindrical tolerance zone for the counter bore at your MMC. Okay, so again, most material condition, we want a lot of the material left on your part when we drill the hole, yeah. So therefore, you're going to have the least, diameter of the hole for that maximum material condition to be met. So when you actually drill it outside, yeah, so you need a drill to drill this. So of course, if you use like a different tool, so that's what it's talking about when you do the operation, meaning machining. Yeah, when you drill it, you can do the operation simultaneously at the same time. Yeah, um, in order for you to have these to have your savings on your manufacturing machining courses. Yeah, it is really important to perform these functions separately. Yeah, you can do it at the same time. You have to do it separately. So what is got to be separated is your clearance hole and counterbore. Yeah, when you drill them, you've got to make it. To do it, because they have separate tolerance. They have separate tolerance zone. Okay, so therefore, when you machine it, you got to do it separately. Okay, that's what is talking about in this slide. Okay, and now we're getting to floating and fixed fasteners. One is a floating fastener and the other one is a fixed one. So let's see how we handle that. Okay, so what I'm going to do here, is going to stop right here at the counterbore before we get into the floating and fixed fasteners, and I'm going to give you a break. And as I have already told you in the beginning of the semester, the material of this class is a lot. Okay, you just have to keep going. So I'm going to stop the second part right here. Right? They're like always at least a 1 hour lecture all the way to 3 to 4 hours. Oh my gosh. It's not easy on me, also not easy on you, not easy on anybody. So anyway, so take a break, and then we're gonna move on to the part 3.